Okay, so we'll continue where we were discussing the last time. So this video we were talking about is about ISO system of limits and fits, and this nomenclature that we are looking at right now is part of something which we are going to do later. So it is important that these all fundamentals are clear.
Fixed, and lower deviation is varying according to the IT grade. And in case of hole, the lower limit is fixed, means lower deviation is fixed, and upper deviation is varying according to the IT grade. Now, all this example we have considered that was of clearance fit and of this pattern.
So the earlier examples, I mean, whatever we have discussed till now in this video was about clearance fit, right? And it's a hole basis system. You can see that shaft tolerance will always be below hole basis, I mean, hole basic size, so that there is no interference. And you can see that it is coming below the white line, which is the zero line. Okay, and blue one is the hole tolerance zone, and below is the shaft tolerance. So basically shaft is below the size of the shaft is below the whole basic size. That's why you will be able to assemble a clearance fit, have a clearance fit.
It was all were below the zero line. Shaft tolerance zone was below zero line, like this. And hole tolerance zone was above zero line, but its lower deviation was matching to the zero line. It means it was the whole basis system which we have discussed. Now consider 50 capital H6 A6. Now here small a, it is representing the fundamental deviation for shaft.
So as we've talked about it yesterday also, the smaller alphabets, they represent fundamental deviation of shaft, and the capital alphabets, they indicate the fundamental deviation of hole.
So if you keep fundamental deviation for whole capital H, it means it is whole basis system. Then the only shaft will be changed to get the required fit. It
So it will be predefined that if it's a whole basis system or a shaft basis system. In whole basis, if it's a whole basis system, the fundamental deviation will be zero for whole, and we have to vary the size of the shaft.
may be A, B, C, D, E, F, G, H up to H. You will get the clearance fit.
So till H you get the clearance fit. Okay. Till the H alphabets, from A to H you get the clearance fit, and beyond H you get transition fit, and there is another set of alphabets which come to get the interference fit. We will see that.
After that, above H, when you go for J, JS, K, M, all this will give you transition fit. Later on, remaining all N, P, Q, R, S, T, and up to ZC belongs to the interference fit.
Okay, so we've understood quite a lot about the IT systems. One more very interesting video is there. Let's have a look at that.
Useful over the years, and I hope you will too. The ISO system. I've wanted to make this video for a while. It's on something I've found very useful over the years, and I hope you will too. The ISO system of limits and fits. Contrary to most of the other videos on the topic, I'll be presenting this with a working microphone. If you've seen as many videos online as I have about this, you'll get that joke. Before I get too far into this, I want to say that this is my understanding of the ISO limits and fit system. and I did do my due diligence to make sure it was correct, but if I make a mistake, please let me know in the comments so I can either add edits to the description, or if I'm way off base, remake the video. So starting off, any dimension in existence has some tolerance to it. The tolerance specifies how much higher or lower a dimension can be from nominal and still be acceptable. The space between the upper and lower limit is often called the tolerance zone. Think about it like football uprights. Each upright represents a limit, upper or lower. To score a field goal, we kick the ball towards the center, but no matter how the ball flies, as long as it ends up between the uprights, it's acceptable, and our parents...
So this is a very good example that he is given. It is about like goal. In the football, there is a goal post. So as long as you are able to do the goal, it is acceptable and it is considered to be goal. Similarly, in the tolerance zones, a tolerance zone and the upper and the lower limit could be considered like a goal post.
Parents will still love us. Before we get any further, I should mention that I'll be talking about shafts and pins fitting in holes, but per ISO 286, this system can be used for internal and external features of size. You'll sometimes see it used for keys fitting in keyways, for example. How things fit together is determined by how much free space there is between the two parts. If there's lots, there will be lots of space for the parts to move. If there's only a little, there'll be a lot less space. Finally, if there's no space, the part won't be able to move. In this video, I'll show the hole tolerance zone is red and the shaft tolerance zone is green. This means that without measuring, the actual outer diameter of the shaft will end up somewhere in the green zone, and the actual diameter of the hole will end up somewhere in the red zone. A pin can fit into a hole one of three different ways: clearance, transition, and interference. A clearance fit means that there will always be space between the two parts, no matter how the tolerances turn out. Transition fit means there's sometimes space between the parts and sometimes there isn't, but it's usually pretty close. Interference fits never have space between the parts, and one part always has to be forced into the other. It turns out these categories can actually be quite broad. For example, a 9mm pin fitting into a 10mm hole is a clearance fit, but it would be extremely loose. A 9.98mm pin in a 10mm hole is also a clearance fit, but it's much tighter. The former might be good just to make sure two parts don't hit each other, and the latter might be good for making sure the pin stays approximately in the same position relative to the hole. Different fits, as well as their descriptions, can be found by looking up preferred fits and tolerances in the Machiner's Handbook. There's a preferred fit for most situations, and this is a really good starting point. Also, check out the YouTube video by Tarka on the ANSI system of fits and tolerances. The designations are different, but the concepts and considerations are the same. So if we want a dowel pin to fit loosely in a hole, we measure it, we ream the hole to have a little extra space in it, and we put it in. The problem arises when you have a bag of 100 dowel pins and you have to ream 100 holes. Dowel pins have a tolerance on them, and their sizes will always vary a bit. Your reamer will also cut slightly different sized holes, depending on your work holding, wear in the reamer, and the cutting parameters, all of which can change while reaming your 100 holes. Because you bought the dowel pins and have no control over their tolerance, this is called a shaft basis fit. So the challenge is now to decide what size reamer to use to make sure that all the dowel pins fit properly. If you know the tolerance range you can expect from your reamer, and you know the tolerances of the dowel pins, you can choose a reamer size where the smallest hole the reamer can cut still has space for the largest dowel pin. This is called the allowance, and is typically something you choose. You're allowing, say, 25 microns of space between the largest dowel pin and the smallest reamed hole. Because there will be other smaller pins and your reamer will sometimes cut larger holes, you may also find yourself cutting the largest possible hole for the smallest possible pin. The extra space on top of the allowance is called the clearance. If the clearance is too large, the fit might not work. The only way to change the clearance without changing the allowance is to tighten up your tolerance zones, either by changing your manufacturing methods or buying tighter tolerance pins. Conveying tolerance zones can be a bit annoying. Say you own a factory that makes dowel pins. You want to be able to tell customers what the tolerance zone is on each size of dowel pin, but it would be cumbersome to have to create engineering drawings for each size. So instead, you can just say the tolerance will always be a bit over the specified dimension, where a bit over scales roughly proportionally to the target size. We can say that all the pins will be between 0.1 and 0.3% larger than the nominal dimension. The problem is we don't want people to have to constantly calculate what these percentages are. The system we use instead is called the ISO 286-2 standard. ISO 286-2 uses numbers and letters to convey tolerance zones, things like M6 and H7. The number, also known as the International Tolerance Grade, roughly indicates how large the tolerance zone is, and the letter indicates roughly where it is. The letter H always means that the specified tolerance zone includes the nominal size as one of the limits, and it diverges into the material. For holes, H means the smallest the hole can be is the nominal size, but it's allowed to be larger. For shafts, H means the largest the shaft can be is the nominal size, and it can only be smaller. The H tolerant zone is important because it's taken as the middle. Shafts or pins with tolerant zones before H in the alphabet will never be the nominal size. Holes will always be larger and shafts will always be smaller. After H, there are a few tolerant zones, such as J and JS, where the shafts can be larger or smaller, but as you go further through the alphabet, the shafts will get larger and larger and the holes will get smaller and smaller. Holes always get an uppercase letter and shafts always get a lowercase letter. Okay, so now we have a naming scheme for tolerant zones. For a given fit, we will usually have one component driving the other one's required tolerant zone. In this example, where we bought the dowel pins, we have no input on their tolerance, so it was a shaft basis fit. If we're designing a shaft that has to fit in a purchased bushing, we can't control the tolerance of the bushing, so we have a hole basis fit. Shaft or hole basis fits often use an H tolerant zone, respectively, since the H tolerant zone contains the nominal size as one of the limits. If we're lucky enough to be designing both parts, we do have some discretion, but you would normally base your fit on whatever side of the fit is harder to change. The preference tends to be designing for a hole basis fit, as in general there tend to be more options for precisely reducing the diameter of a shaft than precisely expanding a hole. So what does a fit look like in the ISO system? It's simply the two tolerant zones specified next to each other. An H7G6 fit means, for example, the hole has an H7 tolerance and the shaft has a G6 tolerance. I've cut some holes in this piece of aluminum to show some examples of different fits. This is an undersized H6 tolerance dowel pin. The E7H6 and F7H6 are reasonably loose clearance holes. You can rattle the 12.7mm H6 dowels around a little bit, and they basically drop right through. The H7H6 and G7H6 are much closer fits, and could perhaps be used to locate parts while remaining removable. The JS7H6 is a transition fit that, as you can see, ended up being on the light interference side, but a rubber mallet would work to tap the pin in for a semi-permanent joint. Finally, the P7H7 is an interference fit and would probably require a hydraulic press, or at least a beefy arbor press to install. This might be a good time to point out that, contrary to my labels in my past example, individual holes and shafts can't be called JF7 or H7. The JS7 refers to the tolerance zone that the hole falls in. A hole that is 10.001 millimeters is in the JS7 tolerance zone, but it's also in the H6, H5, and JS5 tolerance zones. You have to remember that we can't measure the hole until after it's cut, and we have to specify the acceptable tolerance zone before it's cut. The fits also have some range to them. For example, these three holes are in the H7 tolerance zone, and these are three H6 dowels. Note how they fall through the holes at different speeds due to the minute differences in the clearance. The numbers themselves are actually determined by the IT system, the International Tolerance System. Every manufacturing process can be statistically analyzed and an IT number can be determined. This means that if I'm reaming a hole, I can look up the reaming process and see that at best I can achieve about an IT7. So I can't specify an H5 or a G5 hole if it's going to be reamed. Likewise, if you have to design something to fit inside a drilled hole, even if you don't have the tolerance for the hole in front of you, you can look up drilling and see that it has at best about IT10. So the whole basis for the fit is going to be around H10. So why would you use this system? Personally, I like how much information is available through just 2 digits. If I have to make a bearing seat on a shaft for an 8mm bearing, I can simply look up what tolerance is required from Machiner's Handbook or something similar. If I need a bearing seat for an 8mm bearing on a shaft that will see reasonably high loads, I can see that it recommends a JS5 fit. The machinists are not going to be happy about that. I know from the fact that it's JS, it'll probably be a transition fit and might need a little force to install, and the 5 tells me I'll need an IT5 process to make it, which will either involve very accurate turning or cylindrical grinding. As another example, if I want a nice sliding fit and the shaft I require will be in the H6 tolerance zone, I can simply specify a G7 on the hole tolerance without having to estimate how much allowance or clearance I want. Specifying a tolerance zone like this on a drawing does mean that the machinist might have to look up the actual numbers, so typically I include the fit as well as the tolerances. So knowing the different tolerance zones and having a list of a dozen or so preferred fits, we should be able to design parts that fit together how we want. We also have a means of vaguely checking if a manufacturing method will be capable of hitting those tolerances. In addition to the oft-used pin and hole example, the system can be used for internal and external parallel faces, such as keys and keyways, or other features of size. Well, that was a bit of a dry one, but hopefully you found it useful.
So this was a very interesting video. And do you have any doubts in this? Or can we go ahead? Anyone? Okay,
So how many different types of letters are there so that we can classify these tolerances?
So this is all standard. These alphabets which you see, no, these are standard alphabets, and the corresponding size of the tolerance zone with these IT grades are also standard sizes. Okay, so I hope this was your doubt.
Yes, sir.
Okay, so let's go ahead. Now, moving on, how do we use these? And let me show you one more. I think I've already shown you, but it's there in the slides also. Just a recap, that would be. So let me show you that. Yeah. So this is what we were talking about. And now you see that as you move from left to right here, so you're moving from left to right here, you see the shaft's tolerance zone is below the basic size of the hole. And this is a hole basis system, because why it is a hole basis, you can see that the tolerance zone of the hole and the fundamental deviation of hole is 0. When the fundamental deviation of hole is 0 for an assembly, it is a hole basis. And if it's if fundamental deviation of shaft is 0, it will be a shaft basis system. So you can see constantly your tolerance zone of the hole is lying above the 0 size, and as we move from F, A, B, C, D, E, F, G, we reach G, and then subsequently we reach H over here, we start getting, you see, we are getting transition fit. And now you see that the hole's fundamental, hole's tolerance zone has crossed the basic size and has gone above the line, and it's giving the interference fit over here. Okay, so that's how we find out the tolerance zones. Now, after finding out the tolerance zones, the applications of the various, this also we can see. The applications of various fits which we have. You can see here clearance fit. Just for example, H is taken in all, and you can say hole basis and shaft basis. If it's a hole basis system, H11, C11. If it's a shaft basis system, it will be capital C11 and small h11. Okay, so it's not necessary that you can get clearance fit only in the hole basis or the shaft basis, but then the alphabets are going to get interchanged over here. You can see that. Okay, and it's, you see H7 G6 over here and G7 H6. So depending on the kind of fit that you want and your requirement, you are going to choose the type of alphabets. Okay, now going on further, we are going to talk about limit gauging now. This is very important as far as the industry is concerned, because see, in industry a lot of production is going on all the time. Most, I mean, if we talk about mass production or significant size of the production, then if let's say you have to take a measurement of all those things all the time, each item, let's say a factory is producing 10,000 dowel pins in a day. okay, or a significant size of production is there. Is it possible to take measurement of each? It's not possible, right? You just can't take measurement of each and every item. So when you can't take measurement of each and every item, and you want to ensure the quality of the outgoing products, there is something else which you need to do. You have to think out of the box. So we come to limit gauging. So limit gauging is generally used in mass production where large number of similar components are being manufactured on interchangeable basis. And inspection of each unit is time consuming and expensive, very expensive exercise. Also, you are mostly interested in whether the particular size is lying within certain limits or not. You are not concerned about the exact size of the object. And when you just want to know whether the size is lying between certain limits or not, whether there is a goal or not. See, when you're playing football, all you are concerned about is whether it's a goal or not. You are not concerned about how far it was from the goal post when it went for a goal. Or are you getting it? So same things happening in the industry as well. You are mostly concerned whether this is the shaft, okay, and it should pass through this particular hole over here. Okay, and also it should not be too small. So we are, can you suggest anything what can be done? We are not interested in doing the measurement of this shaft which I have produced. I'm not interested in doing the measurement, because if you are going to check measurement of 10,000 shafts or even 1,000 shafts and measurement using a your vernier caliper or screw gauge, whatever you are using, it may take 4 to 5 seconds, if even 4 to 5 seconds, if you are a very proficient worker. So measurement of even 1,000 units. Can you tell me how much time is going to take? If one takes 5 seconds, so how much time is going to take to measure 10,000 shafts?
About 2 hours.
50.
You can say 2 hours, and very optimistic. This is a very optimistic time where he's not stopping at all and continuously working like a robot. Okay. So yeah, so people are saying we should be using go and no go gauges. Exactly, that's where I'm coming to. So we should be using go and no go gauges for such purpose. Okay. So the what happens in go and no go gauges is, let me show a video to you where you'll understand better, and then I'm going to come to our part. So we see here go and no go gauges I'm showing, and in the go and the no go gauges, you look at it carefully how it can be designed, because that is something which we are going to do. We are going to design go and no go gauges for a certain assembly.
Sir, are you presenting something?
Yeah, just a second. I'm going to be starting a video.
go and no-go principle. In this video, we are going to see the principle of go and no-go gauge. Let us see the 3D model of go and no-go gauge. The dimensions of the go end is equal to the minimum permissible dimension, and that of the no-go end is equal to the maximum permissible dimension.
Now, what you see over here is go side and no go side. You see, this is called, the one that you see on the screen, this is called a plug gauge. Plug gauge because you're going to test size of you can say shaft. I mean, your size of a hole you're going to see. If let's say I have produced a hole, you see over here, the workpiece has been made, cylindrical hollow workpiece, and I want to test the internal diameter of the workpiece which is produced. So I can use plug gauge. That is, this is called plug go and no go. Why plug? Because it's being used as a plug to go inside the hole. So if it is a go, if it goes inside, what does it mean? I mean, I'm going to design this go gauge in such a way that if it goes inside the shaft, it ensures minimum permissible dimension. And if it doesn't go in the shaft, it ensures maximum permissible dimension of the hole. Do you get that? Imagine if this is going inside, and if this is going inside, then that means minimum permissible dimension. What is the minimum permissible dimension of a hole? Lower limit or the higher limit of the hole? Tell me. What is minimum permissible dimension? Should it signify the lower diameter or the higher diameter of the hole?
मिनिमम अपर होगा, मिनिमम वाला अपर.
Minimum permissible dimension. Yeah, higher limit is going to indicate the minimum permissible dimension, and if it is not going inside, that means maximum permissible dimension. What is the maximum permissible dimension? Upper side. If it is not going, that means your hole which you have produced is smaller than the highest size which was permissible, or your size of the upper limit, or you can say the upper limit of the tolerance zone. You can always imagine it. If let's say you have you can use it, pen and a cap is there in front of you, all of you are having that. So if the pen is not going inside the cap, what does it mean? Does it not mean that the maximum size of your hole is smaller than the no-go shaft? Does it not mean that? Yes or no? I mean, how many of you are understanding this concept? Say yes if you are understanding in the chat box. Write in the chat box if you are understanding it, yes. Only Sagar has said. Shailesh has said. Yaya Ansari, Govind, Chitrang. So only these many people are there listening to the lectures, I think. Either say yes or no. If you're not understanding, I can explain again. If you're saying yes, then I'm going to go ahead and assume that you've understood it. So Pratik is saying no. Okay, Pratik. Okay, so let me repeat that again. Now imagine we have to check. I produced a shaft. Okay. Now I want to check whether the shaft which I have produced is within the upper and the lower limit or not. Okay. So to check that, I devise a go and no go gauge. Now, if this go and no go gauge which I have devised, I'll use it as a plug and insert it in the shaft which I produced. So when I'm going to insert the shaft in the hole, I'm going to, if it's not going inside, if not go side does not go inside the shaft, what does it mean? That the size of the hole is smaller than the no go size. Okay, this is one. So when it is smaller than the no go size, it means that the maximum permissible dimension of the hole, which should have been the highest, is smaller than the no go size which I have designed. Similarly, go shaft should go in, which will indicate if the shaft is going in, that means it is larger than the smallest size permissible. Okay, the smallest size of the hole which should have been.
Excuse me, sir.
Yeah,
We are checking the limits of hole or the shaft from this go and no go gauge.
hole. See, I'm going to produce this go and no go gauge. I'm going to make this go and no go gauge specially for the dimension which is being mass produced. And the dimension which is being mass produced over here is the cylindrical object which has got the internal diameter. So I'm more interested in the internal diameter of this. And if I'm interested in the external diameter, I'm going to use ring gauge, where the outer side of the outer dimension of the cylindrical object will be checked. So it is like a ring. You insert the whole object in the ring. Okay. So plug means you are plugging it for the internal dimensions, checking the internal dimensions of the cylinder. Okay. So one more video I'm showing, which might make it a bit clear. So let me complete this one first.
Workpiece. First, we see no-go process. In this case, the no-go end
See, it is not going inside. Okay.
must not go into the component feature. Now see the go process. In this case, the go end of the gauge must go into the feature of the component. Therefore, the component being checked.
So it checks either of the things. It checks both the things, if it goes inside and if it doesn't go inside. Okay.
Taylor's principle. In this video, we are going to see about Taylor's principle. It states that the go gauge must be made to check the maximum metal condition. It is marked in green line.
So go. What is the maximum metal condition for a shaft? I mean, for a maximum metal condition for a hole. What is the maximum metal condition for a hole? Lower limit.
Lower
or-
limit.
Yeah, lower limit. Okay. So go gauge is going to check the lower limit of the what? Go plug gauge is going to check the lower limit of the shaft, or you can say maximum of the hole, and the maximum metal condition for the maximum metal condition.
The no-go gauge must be made to check the minimum metal condition. It is marked in red line.
So this is the Taylor's principle, which says that go gauge should be made for maximum metal condition, and no go gauge should be made for minimum metal condition. If it's shaft or a hole, irrespective of that, it's always going to be the same. So I repeat that. The Taylor's principle says that the go gauge should be made for maximum metal condition and the no go gauge should be made for minimum metal condition.
Component. The go gauge should be as far as possible the geometrical shape of the components to be checked. This also checks at a time straightness or parallelism of the hole over its full length. For circular holes, the no-go gauge should be a pin gauge.
आप वॉशिंग मशीन यूज करते वक्त
Okay, so one more video I'll be showing.
Excuse me, sir.
Yeah.
So in this video, it said that the go gauge should be made for maximum metal condition.
Yeah.
So is it only for holes or for hole and shaft both?
It stands for both. This is a Taylor's principle.
Okay, sir.
So I'll show another video is coming up.
Double-ended plug gauge. In this video, we are going to see about double-ended plug gauge. In this type, the go end and no go end are arranged on both the sides of the plug workpiece.
I think this is already we have seen. Just a second. This one has already been seen. That video is missing somewhere. Anyway, so we'll continue. Now the idea is that what idea we have received is that we should be according to the application. If I'm talking about measuring the hole or measuring the shaft, my go and no go gauge should be designed accordingly. Okay. Now going ahead. So we can try to make the sketch over here. You should all make this sketch because it will give you some confidence in what we are doing. So let's say metal limits for hole gauging. So let's say this is the MML I'm going to write maximum metal limit, and this is a hole. So correspondingly, if I want to make a, let's say this is your upper limit. So if I am going to make a go gauge, it should be somewhat like this. It should be designed for maximum metal limit, go gauge. And your no-go gauge should be designed for lower metal limit. Okay, so this is your lower metal limit of hole. And this is your maximum metal limit for hole, this one. So your go gauge is designed for MML and your no go is designed for lower metal limits. Can you similarly make metal limits for shaft gauging? This is for hole gauging. Now try to make it for shaft gauging similarly. So if you have to gauge a shaft, that means you will be needing ring gauge. That means like here you have plug gauges, go and no go. Now you will have ring gauges which will slide over and not slide over the shaft. Metal limits for shaft gauging. Okay, now try to make it on your own. See your sketches in the WhatsApp group. I will see if how many of you are getting what we want to do. Yeah, I'm looking at it. Let's see how many of you have sent it. So 6. Adnan has sent it. Okay. On one side you made go gauge, and another side you made not go gauge. So, see, it should be like ring around. So how should you make a ring? This is how a ring should be made, no? This is a ring. In a way, if you look at it, this ring would be somewhat like this, and it's going to pass over the shaft. If you isometric figure, if you want to make something like this, so it is going to cross the periphery. None of you are making the ring. Try to make it in a ring way, then only you will be able to understand. I'll anyway make it, but as long as you are making it, you will always be confident. Okay. Okay. The last one has sent it fine. It looks fine. The last one. Okay. So let me make it now. Let me make it easy for you. So it's going to be, let's say this is your shaft which you want to check. This is your shaft which you want to check. Okay. And this is the lower metal limit of the shaft. And this is your maximum metal limit of the shaft. Okay. Now the go gauge should be designed for maximum metal limit or lower metal limit?
MML.
Yeah. So this is your go gauge. And your not go gauge would be for, you can say this is for not go gauge. So you can see here, this is the ring. You can say like this. This is your, these are two of your rings. So this is a not go gauge. Which is going to not cross the shaft. Okay, for the lower metal limit. So it's a lower permissible values of the dimension are going to be checked by not go gauge, which is a ring over. It's a ring type of, it's a ring gauge, and if you are checking the size of the hole, it is a plug gauge. So ring gauge and plug gauge, I'm writing it. Ring gauge, we use it for not measuring but gauging limits of shaft. And plug gauge we use for gauging the limits of hole. Okay, now let's go ahead. So some considerations which should be there while we are making the gauge is, first is that the form of the gauges should be replica of the form of the opposed mating parts. So if it's circular, it should also be circular. Or if you're checking it for a rectangle, it should be in a rectangular form. Okay, so that's pretty obvious also. Go gauges should enable several related dimensions to be checked simultaneously. Like it was there in the video, when you are inserting the plug gauge in the hole, the go gauge was also, besides simply checking the dimension, it was also checking the circularity and straightness of the object, of the hollow cylinder. Okay, so the second point says that it should be able to check the related dimensions also. Similarly here, ring go gauge it's also going to check circularity, and at the same time it's going to check straightness also. So if it is not straight at any point of time, the ring may not pass across, or it may get stuck a bit. Okay, even if it is passing. So that thing should be clear. And not go gauges can check only one single element at a time, unlike go gauges, because they are not going to pass through the profile of the object. So it's going to check only one type. Okay. Now what should be the material of these gauges? Can you tell? Material properties of these gauges. What should be the material properties of these gauges? Anyone? Not get deformed easily. Now let's see, we are all mechanical students, right? So we should be able to take some technical names.
Large hardness number.
Yeah, so it should have hard and wear, they should be hard and wear resistant. They should be hard and wear resistance for the simple reason that they have to slide over the objects continuously all the time. Okay, so otherwise their dimension may reduce over a period of time. So it's like if you have made go and no go gauge, it is a very high, we use very high degree of tolerances in making. We have seen that earlier also, that when we are that the tolerance grade for these kind of applications are very high, IT0 kind of grade. Okay, so if we are giving that close tolerances, that they should not fade away quickly, otherwise your whole production lot, like on a given day you used a worn out go and no go gauge, and you've done the production and you check the size of the shafts. Because of the wear and tear, one day you have accepted all the lot which is going to go for further production or to the consumer. It may be a big disaster also. Okay, so one is, then it should be have the capability of maintaining dimensionality, dimensional stability and form. So we can also say that it's simply hard and wear resistant. Fine. Corrosion resistant. Say again the same thing, if it gets corroded, then it may change the dimension. Okay, if you see rust is forming over the object, it might increase the dimension of that object. So some people are saying low coefficient of expansion due to heat. Very right. So that's good. Low coefficient of expansion. low coefficient of expansion. What about machinability? Low surface roughness, Ananya is saying. Yeah, right. So surface roughness, but does the surface roughness depend on the material or does it depend on the machining? Tell me, Ananya.
So, sir, materials ability to be machined.
Yeah, so machinability, right? We can say easily.
Yes, sir.
Yeah, so easy machinability. Okay, so these are the some properties which we can say that should be there for gauges. Okay, now we talk about now in next class we are going to start talking about how do we design it and what are the allowances or the you can say when I'm producing it. So what are the allowances I have to apply on it, and the whole designing part of it we will do in the next class. So we will design a go and no go gauge in the next class. Okay, which is if I start right now, it will be all gone because we need one whole class to do this designing. Okay, so if you have any doubts, let me know and you start giving your attendance. Start giving your attendance now, and that's it for today.